Good afternoon. We will talk about other components of resistance. We have actually seen how the frictional resistance around a ship can be estimated. We have seen the physics of wave making around a ship hull form. We have also seen that waves, when they interfere with each other, it can be supportive to motion or opposing the motion. Basically, we have seen that wave making resistance has a component, a major component, which is proportional to speed raised to the power 6, and over which there are small humps and hollows created due to interference of the bow, stern and aft shoulder, forward shoulder waves. This is what we have seen in the this thing. Now, can we utilize this interference in a manner that we can reduce the bow wave component itself? We have said before that if I have a submarine below the water surface, I will still have a wave effect just below the water surface, because the depth is not very large. So, the wave effect will not be there. Can we utilize this? For example, I have got a ship which generates a bow wave system. Can I have a body, a sphere for example, somewhere below the surface in the front of the ship, which is placed in such a location that it creates a wave trough where a bow wave crest existed? Is it possible for me to do it? That is, if I have a bow wave like this, can I have something which will create maybe a wave like this? If I can, then you see this much will go out. So, I will have a much reduced bow wave. And if I can design something which will generate me a wave of this shape. So, this wave may come from a ship like this, moving at this water level, and this may come by putting a sphere here, and so I generate a bulbous bow. Bulbous bows have been in existence for a long time. People did not know what is the effect of bulbous bow, but today it is fairly well known that ships who have a large component of their resistance as wave making resistance, if we have a forward bulb, then that can be controlled. As I told before, please do not think that you can make the wave ship's free surface totally flat and wave making resistance 0. That is not possible. What we can do is we can reduce the amount of wave making by reducing the forward crest of the bow wave, which is the prime component of wave making resistance. And ways of doing it is by putting a bulb in the forward end in a manner that the crest of the bulb opposes the crest of the bow wave, or crest of a bow wave superimposes on the trough of the bulb, if I could do like that. Now, it has been found that if you give a bulbous shape, this happens, the crest height reduces. The bulb, you have to be very careful in designing it, because it can also add, as you have seen. So, we have to be careful in designing in such a manner that the total height reduces. What other effect the bulb has? I am bringing down the volume below by putting a bulb here. The volume that was here, I have brought it down. Do you understand that? My underwater volume increases. Therefore, the volume distribution of the free surface, area distribution of the free surface reduces. So, now I am in a position to give a waterline which is finer. Can you understand that? If I draw a section here, it will be like this. right. If I draw a section here, it will be something like this. So, you can see this and this are my waterline widths here. So, if I draw a waterline here, it will look something like this. This is my half angle of entrance. If I did not have this area below, then how would my section would have looked? Like that. That means I would have had this breadth at this point. That means I would have had a large breadth here. I talked about half angle of entrance. You can see by putting a bulb, I am reducing the half angle of entrance considerably. Because I am reducing this, I can also smoothen my shoulder. Do you understand? So, I can do a lot of design exercise. If I put a bulb, my water line is more nicely shaped and supports reduction of wave making resistance, apart from the interference effect. But one has to be careful that the bulb does not add the crest due to the bulb wave and the ship bow do not coincide. Is that clear? So, that is interference. So, this is one component of the other component, the so called other components. We have the wave, this is all part of wave making resistance, but wave making resistance is, as we have seen, is proportional to V to the power 6, a constant power, plus interference due to 4 wave systems, 4 oscillating terms interfering with each other and giving a addition to wave making resistance. We can design a ship with a bulbous bow in such a manner that these oscillating terms can be drastically reduced. Okay. So, you can get some support by designing a bulb. Bulb has also other effects. We will see that a little later in this lecture itself. We have seen that Ct is equal to Cf0 plus Cr, where Cf0 we have said is the ITTC based frictional resistance coefficient, which is primarily the 2-dimensional frictional resistance coefficient, right. Now, about the ship shape is actually 3-dimensional. There are 2 effects that happen. One is that the compared to a flat plate, the water line has to travel a longer distance because the ship is curved. A flat plate and a curved plate. If I take the same length, because Reynolds number is dependent on length, the Reynolds number of the flat plate and the ship is same. For the same Reynolds number, if I take the same length, then the water has to travel this distance, whereas here the water was traveling only this distance. Is that right? So, therefore, there will be an addition to frictional resistance in 3 dimensions. In fact, I have drawn it in 2 dimensions. In 3 dimensions, when there is a vertical component also, that water the length that a water particle travels will be still more. Understood? Also, another thing will happen, as we have said before, because of the existence of a boundary layer, the pressure distribution will change as we go to the aft. Forward end, the boundary layer is non-existent, but as we go to the aft, the pressure distribution will change, and that will change the velocity magnitude of the water particle on the ship form. So, you will have generally a higher velocity in the midship region and a lower velocity in the aft region. If this happens, the frictional resistance will change again, because it is a function of velocity after all. So, there will be, this is called the friction form effect. Okay. The effect is primarily 3-dimensional effect over 2-dimensional effect. So, if I write total frictional resistance as Cf, I would like to write it as 1 plus k Cf0, where k is the form factor. And one assumption I make, this is independent of speed. Okay. Let us see what happens to pressure. I have got a ship here. Let me draw a ship. This is a ship going in this direction. A boundary layer develops. And it does not close at the end. There is no way the boundary layer closes. This water inside the boundary layer is being dragged along with the ship, because the water is having less speed than here. Okay. We have also said that the boundary layer is defined, thin boundary layer is defined by definition. The flow beyond the boundary layer thickness is of potential nature, isn't it? We have said that the nearly total velocity, fluid flow velocity is reached at the end of boundary layer. What does it mean? Flow beyond this is potential nature. So, what happens, strictly speaking, as if the body is elongated, instead of being this body, it becomes this body, right, with slopes much less than the original body. So, the pressure distribution changes than if there was no viscosity, and since the slope reduces, the contribution of aft body for aft pressure forces for reducing the pressure, reducing the resistance reduces. So, effectively you have an augment on the pressure resistance because of the existence of boundary layer. The waves get damped. Pressure is getting damped actually, high pressure is becoming slightly lesser pressure. So, the wave that would have been created by the stern wave has now got damped. Am I clear? So, this is adding a portion to the total resistance, because the support that it would have given is not there anymore, it is reduced. So, the augment of pressure due to existence of boundary layer is called viscous pressure resistance. Okay. So, you have this, you have the viscous pressure resistance, and apart from that, because of the shape of the body and boundary layer, you also have eddy or separation drag. What is this? What is this? We have seen that the slope of the body is an important parameter in determining what should be the pressure on the body, right. When we talked about wave making resistance, we said slope of the body determines the pressure distribution. In the forward part, pressure increases if the slope is more. In the aft part, pressure may reduce if there is a drop in. You remember the pressure curve, there is a peak in the aft, but just forward of aft there is a drop. At that place, if I have large curvature, then the pressure will drop further. Pressure will drop means velocity will increase. Imagine the other way, pressure increases because of the slope closing the aft of that drop. If you consider aft of that drop, pressure will increase because of curvature there. If the pressure increases further, then the velocity will drop. There may come a point when velocity becomes 0. If pressure drops to pressure increases to a large extent due to curvature of closing of the body, the velocity may come to 0, and if the pressure increases further, the velocity may reverse itself. That is, I will explain this by means of a diagram, you will understand. Now, we have a boundary layer developing around the body. Okay. If I take the velocity profile here, since the ship is going this way, if I take a velocity profile here, it will go like this. This we have seen, this is the velocity profile, the water flowing past like this. At the end of the boundary layer, it is nearly equal to ship speed. Okay. Here also same thing, but now slope has not started. So, let us repeat this. Now, it has started sloping. So, what will happen here? If I draw a velocity profile perpendicular to the ship hull, there is an increase in pressure. Therefore, decrease in velocity, and that will affect the point near the body. So, instead of going like this, it will start going like this, where this velocity is reduced. Okay. Go a little further down, you will get a point where the velocity will be 0. And if you go further down, the water will start moving in the direction of the ship itself. Do you understand? This is happening because of the large slope of the body here, large curvature. So, what happens? As if a layer is being formed here, with this being the 0 velocity point, where this flow is separated flow inside the boundary layer. Clear? This is the point of separation. Now, this separated flow will affect this portion, it will affect the wave making, it will affect the potential flow, all that will happen. But basically, the small vortices will be formed inside this, who will take more energy than what the boundary layer alone would have taken. So, you will have this drag coming up for bodies that are blunt. The same thing will happen in the forward end. Mind you, forward end is no different. If I have large slope at the forward end, then the water will find it difficult to negotiate the large curvature and you will separate. Typically, if I have blunt end at one extreme, if I say, the water here cannot turn like this, the smooth flow will be like this, but within that this will separate here like this, and similarly here eddy will be formed. Okay. So, there will be two points of eddy making here, as you can see on a blunt body. It can also happen underwater, when I have mentioned this to you before, near the bilges, forward bilges. The flow cannot negotiate the sharp curvature at the bilges, and it will separate. Same can happen in the aft end. Clear? So, you will have this separation drag, which will be a part of the total viscous drag. Then you will have, we have mentioned this before, wave breaking resistance. The breaking of waves due to steepness of the wave, the slope cannot be, wave slope cannot be maintained by the wave itself. So, the wave breaks. This will happen when the waves generated has a shorter length and larger height, and this is a phenomenon typically of full form ships having very large angles of entrance in bulk carriers and tankers. wave breaking can also occur at the stern. Stern wave can also break for the same reason. The point to note is that wave breaking also will reflect itself in viscous resistance, and if we can reduce the pressure distribution around a blunt form, then it is possible to reduce the wave breaking resistance itself, because there will not be any wave breaking. If you can reduce the wave slope by reducing the height of the wave generated, then it will not break, and then we may reduce this component of resistance. Why I bring this up? We talked about bulbous bow at the beginning. We said that when the wave making is large, if I put a bulb, then wave making will be reduced. Now, if you take a container ship with a Froude number of about 0.3 or a passenger ship, wave making resistance will be nearly 60 to 70% of the total component of resistance, and by putting a bulb, we can reduce that component of resistance, frictional resistance remaining more or less same. But when you come to a tanker or a bulk carrier, a super tanker or a bulk carrier, which has a Froude number of 0.15 to 0.2, moving at very low speed compared to its length, we are talking of 200-250 meter ship moving at 14 knots, 16 knots, you can calculate the Froude number is very low. Wave making resistance is only 10 to 15%. Most of the resistance is viscous, but we still find ships with bulb there. Why do we have a bulb there? The bulb basically reduces the steepness of wave making at the forward end, and therefore, this component of resistance, wave breaking, reduces. The resistance created due to breakage of waves comes down. So, we can reduce that also by a bulb. So, bulbs are today used across the ship forms for high speed forms as well as for low speed forms, but the design considerations are different, where there you are trying to reduce the wave making itself, here you are trying to reduce the wave breaking. Okay. Now, we talked about form resistance, and we said that the form resistance is primarily the 3-dimensional form resistance, 3-dimensional effect on friction. But we have got these other components of viscous resistance now, viscous pressure resistance, and we have got wave breaking resistance. Where how do we take this into account? We take all this into account in something called form resistance. Do you understand me? Now, let us say there is a little gray area here. I want to make it clear that there is a gray area. If I draw the CT curve against speed, if you remember, the CF curve would have gone like this, CF 0, okay? And we said that the wave resistance at the low speed range will first, the coefficient of total resistance at low speeds when there is no wave resistance will follow the CT curve, right, and then it will go up like that. This is what we have said, and therefore, we had said that when the wave resistance is 0, that CT, this we had called C form, right. Am I correct? And this then we had said as wave making resistance or CR, let me call it CR, and this CR was primarily wave making. Now, we have talked about other resistance components like separation, we have talked about wave breaking and all this. How do we represent them in this diagram? Whatever component of resistance existed at low speed, we have taken this into account here, and those components of resistance that come at higher speed, they are not represented in this line. So, perhaps they are represented in this residuary resistance component. Are you getting me what I am saying, or not? What is this C form? We have defined it as the 3-dimensional friction form effect. That is, C form we have said is equal to 1 plus k Cf0. So, total frictional resistance is 1 plus k Cf0. But now we have said about other small components of resistance which may exist, like separation drag and like viscous pressure drag, etc. We are not very sure that this C form has some of these components. So, maybe they are in this CR, where the major component of CR is wave making resistance. So, it would not be fully scientifically correct if I say CR is equal to CW and C form takes all other components of resistance. That may not be fully correct. Therefore, to this extent we can say C form is the form component which takes into account the major difference, major portion of the augment of resistance, augment of viscous resistance over 2-dimensional form factor, 2-dimensional friction resistance. Do you get my point? That is, C form I can say is mainly augment of 2-dimensional frictional resistance on total viscous resistance. Okay. So, we can say C form includes the 3-dimensional friction form effect, it also includes some amount of separation drag component and viscous component. Imagine separation we have said is related to velocity and pressure, they will change with velocity of the ship. So, if it is something at low speed, it cannot be the same at high speed. So, truly speaking, we have not taken this totally into account. That is why I am saying mainly, the word mainly is important there, it is not total. Why is this important? Why are we talking about this? Because this forms the basis of extrapolation of resistance to full scale. We have said at the beginning, a theoretical exposition of resistance is till now impossible. Errors are too large. Therefore, we have to have an experimental method by which we can estimate resistance of a ship from model and extrapolate to full scale. And this is all important for full scale measurement. That is why this is being talked about. Okay? You can imagine, as the ship becomes fuller and fuller, this component starts playing more and more role, and therefore, we get into an inaccuracy zone which is higher as you go to fuller and fuller ship. For example, if I have a barge with a flat ended barge where there is large amount of separation at the front end, this method of extrapolation may not be very accurate. Do you understand? Fruit's method of extrapolation works very well for normal ship forms, where the components of resistance we have defined, that is separation drag, the viscous pressure drag, etc., wave breaking drag, are small compared to total resistance, and we have taken that account in some form in this C form. Is that clear? Okay. Now, what are the other components of resistance that we are interested in when the ship goes to sea? We have talked about correlation allowance. Did I talk about it before? I think I did. That is, when you do a model experiment, the model is very smooth, and when you come to a ship, a new freshly painted ship, the smoothness of that surface is slightly different from model. So, to take into account the roughness of the surface, we put a small allowance called CA or correlation allowance. CA equal to 0.4 into 10 to the power minus 3. This is standard recommended by ITTC, but ITTC in 1978 has updated it. We will see that later. You can imagine that if the ship is very long, you have a CA of 0.4 in 10 to the power minus 3, also if a ship is very short. But you can imagine that roughness will play more role in a shorter ship than in a longer ship. So, roughness allowance will be proportional to or will be somewhat dependent on length. So, now ITTC has given a formulation for correlation allowance which is dependent on length, that is given in 1978 ITTC resolution. Okay. Then for trial condition, for ship trial, there is another component of resistance which we must take into account, that is air resistance. When we talk of resistance to air, we will mainly consider air coming from front, and we will not consider the waves generated due to wind. Suppose it is totally calm, there is no wind and a ship is moving, will it experience any air resistance? It will experience the same way as water resistance, that body is moving in still air as if air is moving past it in the other direction. So, in still air, air velocity is equal to ship velocity. The relative velocity of air with regard to ship is equal to ship speed. But if there is a wind blowing, then if it is a wind blowing head on, then it will be added to the ship velocity. If it is supporting, it will be subtracted. But if it is wind blowing at an angle, then you can resolve it. If the wind is blowing like this and the ship is going like this, therefore, the wind is coming like this, and the component of resultant component will be something like this. You can actually calculate the resultant wind velocity, on the basis of which you will calculate resistance. Clear? Okay. Now, we are mostly interested in the drag to forward motion. So, wind coming from front. When wind is coming from front, what is the windage area that it faces? Let us see, the ship is like this is the upper deck, there may be a forecastle, right, there may also be a bulwark, and the wind is blowing from here. So, that entire frontage of the ship above the lower line will come into play, right. If I draw a section of that, and this frontage will increase as you go forward to a full midship section, midship body. So, the frontage, the middle of the ship looks like this. This is the waterline, okay, and this till here to look something like this from front if I look. Do you understand? So, the transverse area projected to the wind is this area, this point being this point. Then you will have far away from here, you will have the superstructure here. Okay. Now, this superstructure will start from somewhere here, it will go up something like this, right. So, this much of superstructure you can imagine to be protected by the ship. Truly it is not, because the distance is large, but temporarily we can assume that this is protected and this is the area. So, if I call this A1 and this as A2, then the resultant transverse area can be written as .3 A2 plus A1, that is 0.3 times this area into this area plus this area. So, this is the total transverse area used for calculation of air resistance. I am not saying this is a scientific method, I am saying this is the transverse area used for calculation of wind resistance. And wind resistance to forward motion, if the wind is blowing from front, is given as I am just giving you a formula. Wind resistance is fairly complicated, but I give a formula. Why a formula? Because when the wind is flowing past the ship, unlike water, it is not flowing past a streamlined body. The transverse area is not a streamlined body, it is all flat superstructure. Take for example superstructure. It gives mainly eddy resistance rather than nice pressure resistance. Most of the resistance caused due to wind are because of the blunt body, so you have separation and eddies. So, this can only be estimated by experiments. So, a lot of people have done wind tunnel experiments to find the wind resistance, and statistically it has been shown that wind resistance R A A is normal representation is R double A is K rho A T V R square, where V R is the relative velocity in the direction of the axis. A T is calculated like this, rho is the air density equal to, how much is the rho? 1.223 kg per cubic meter, and K is a constant equivalent to a drag coefficient, which is given as 0.6. So, this is the total air resistance, is given as 0.6 rho A T V R square, which if you take the rho air as this, then R A A can be given as 0.734 A T V R square. Now, there is a very interesting phenomenon in the wind resistance case. If the ship is very tall, if it has got large windage area on top, then there is a problem, because the wind velocity changes from the water surface to a height. Water surface, you can imagine there will be friction between wind and water. So, theoretically the wind velocity is 0, and it will very quickly pick up to full speed. So, if I draw a height wind velocity in this way and height this way, then wind velocity will go like this. Okay. So, therefore, the area near the water surface will have less effect than air far away. That is why in this AT formulation this is taken into account by reducing the lower end of area. Okay. If there is a tall ship, then you must calculate the height based on this formulation. There is another problem with wind resistance. Suppose the wind is blowing at an angle. The ship is a long narrow body. If the wind is blowing at an angle, then it generates some sort of a perpendicular force equivalent to lift. If you have a long narrow body and fluid is impinged upon it at a small angle, then you generate a perpendicular force which is called lift force. So, same thing happens in ships. If the wind is blowing at an angle, then the axial component of velocity, the resistance that you calculate by using this formula at an axial component as the axial component, you will find actual axial resistance is more than this. Till about 30 degrees of angle of attack, the wind resistance will increase, then only it will decrease, and mostly in the beam wind condition it will be very high. It will not decrease, it will increase slowly, because as the wind direction changes, the area exposed to wind increases. Beam wind condition, you get maximum drag in that direction, transverse direction, axial drag in 0. Okay. Is that clear? So, this is wind resistance. When you do the trial speed prediction, you have to add the correlation allowance and the wind resistance allowance due to wind, because I mentioned to you that normally the trial condition is specified as at 0 before or before 3. So, 0 before wind speed means wind speed is 0. So, the relative velocity of wind is equal to ship velocity, and if it is before 3, then you have to add the wind speed to the ship speed and do the calculations to get the total wind resistance. It is assumed that at before 3 the C condition does not change. If the C condition changes, or at C whether there is wind or not, but there is wave, maybe a swell, maybe a wavy condition created by a wind which has blown away at mid seas, then there is an augment of resistance due to, it is called resistance in waves. The ship already has waves, it is not the ship waves, the ship sea has waves and the ship has to negotiate the waves, then there is an augment of resistance called resistance in waves. Now, this is something which is not required in trial condition, because normally we will take out a ship for trial when it is the sea is calm, but in service this will invariably be there at sea. So, we have no way of knowing what is the resistance of a ship in a random sea condition, or even taking a simplest case of a sinusoidal water wave, whether what will be the augment of resistance for a ship moving in a wavy condition where the wave profile is sinusoidal. We have no way of knowing. So, most of these are experimental, and we have to do large number of experiments to know what will be the augment of resistance in various wave conditions. Such experiments have been performed on series 60 ships in the David Taylor model basin in USA in the 60s and 70s, and data is available for average increase in waves in various sea conditions. As I mentioned to you, the sea conditions vary depending on the sea itself, apart from the time of the year, etc. For example, North Atlantic is generally rougher than the Pacific. So, the augment of resistance in North Atlantic will be more than in Pacific. So, to avoid doing a theoretical calculation which is inaccurate and not available, and also the sea condition is not exactly known, what we do is we add a percentage of resistance to get the resistance in service condition. Normal standard is about 15% increase in the resistance that we have estimated as the service allowance. That gives us the resistance in actual service condition. We have not talked about the appendage drag. I had mentioned it to you before, but we have not really talked about appendage drag, that is attachments to the ship on the outside of the hull, and typical attachments that merchant ships have or conventional ships have. Let us name a few. First that comes to mind is bilge keel, right. Then you have rudder, yes, sorry, A-frames or shaft brackets, shaft bossings. In naval vessels you may have sonar dome. Then you may have other attachments such as bow thruster tunnel. A tunnel in the forward end to provide a bow thruster will add to the resistance. So, most of these add to the resistance. And how do they add to the resistance? These bodies being small, if the water flow past them is streamlined, they will add only to the frictional resistance. So, you know the Reynolds number at that point, you assume the flow to be turbulent, calculate the wet surface, and based on the wet surface get the Cf and multiply by the wet surface, you get the frictional resistance. Since they are submerged, there will not be any pressure drag due to this. but it is not so simple, because unless it is in the orientation of this is streamlined by itself and oriented in the direction of the overall streamline of the ship, the flow will be disturbed and they may create eddies and separation. So, there may be added drag. To know the streamline shape in the towing tank, we do what is called a paint flow test. So, by the flow of the paint, we can see the direction of the flow and orient our appendages in those directions. But certain appendages such as sonar dome cannot be oriented, because it is a spherical structure. Wherever you put it, it will create eddies and separation. The only thing you can do is see that the quantity is less, the drag due to this is less. Or bow thruster tunnel, it will definitely create some local separation of flow. So, there are some formulations given by various authors for estimating the drag due to each of these in various literatures, the most famous one being given by Holtrop and Mannen in 1984 in the International Shipbuilding Progress, that came from the Netherlands Ship Model Basin, NSMB. But other people have also given formulations. You can find the formulations from various literature for each of these separately. Alternately, you make a model with appendages and do the testing, so that you get the model with the drag with the appendages. There is a problem here. We have already discussed for a normal ship how difficult or how accurate it is to extrapolate to full scale. In the we have said the C form form coefficient we have talked about, we have said there are some inaccuracies and it is not exactly understood. On top of that, you have now added appendages. So, extrapolation may create problem. So, to be on the safer side, one could do a naked hull resistance test and another the hull modified with appendages and test it. So, estimate the appendage drag separately and extrapolate the ship's naked hull resistance separately and appendage resistance separately and add them together. That is another way you can go ahead and do it. So, these are some of the methods by which the ship resistance can be estimated and extrapolated. We will talk about extrapolation once again, because that is the most important thing, accuracy of the extrapolation method to full scale for power prediction. We may look at this if time permits once again later on. What other resistance can be there? Can you name? For very high speeds, there may be a spray drag, or if the rudder or some such appendage is piercing the water, it may generate spray. So, there can be sometimes a spray drag, but normal ships do not have this, and even then the spray drag may be of less magnitude. So, we do not normally consider it. And if we go for higher speed, the high speed crafts, the resistance characteristics are quite different, and we will talk about it when we talk of high speed crafts. Thank you. Good morning. Today we will talk about model experiments and extrapolation to full scale. Of course, our model experiments will be limited to resistance test only, and sometimes this experiment is called towing experiment, because as we have defined resistance before, it is the resistance of towing a vessel without its propeller working in water. So, sometimes this is called towing experiments or resistance due to towing a model in a tank. Why do we require model experiments? One, of course, we know is to obtain the resistance of the ship in full scale. There is another reason why we do model experiments. As I have explained earlier, we know that the resistance of a vessel cannot be accurately predicted by theoretical means. This also means that we cannot calculate the flow characteristics of water around the ship hull theoretically very accurately. We also know that if the flow characteristics are bad, then resistance may go up substantially. So, it is sometimes necessary to do model experiments to find out how good the flow is around a ship, and if the flow is not as we have desired, it may be necessary to change the model shape at particular locations, or even change the entire forebody or aft body of the model till such time that we can get a better flow, hence less resistance. Flow is important not only from resistance point of view, but also for many other problems such as flow induced vibrations. Imagine a strut projecting out of the ship for some purpose, such as forming a bracket for holding the shaft. If the bracket is not aligned in the direction of flow, there is bound to be eddy shedding or separation near the bracket, in the aft end of the bracket. This separated flow may cause flutter of the shaft bracket or vibration. Similar thing can happen due to flow around a rudder behind a ship, or due to unevenness of flow there can be vibration of the aft body which is not fully supported by buoyancy, that is the overhang of the aft portion. So, use turbulence stimulators. Turbulence has to be stimulated. We have to stimulate turbulence in the fore part of the ship. And how do you do it? We will have to introduce artificial roughness at the front end of the ship, so that the flow becomes turbulent because of existence of rough surface. As if we are introducing forcible turbulence on the ship forebody. And what we use is called tripwire. This is the normal turbulence stimulator used in ships. That is, I got a ship model here. I can put a wire right on the front of the ship, or if this is the FP, about 5% length aft of FP, LWL, length on water line. Normally model test we use length on water line. So, I can put a trip wire here, that is, if I draw the section here, the section of the ship may be like this. I put a small trip wire all along the model with small anchors holding it by pins. If I have got a wax model, I can put pins and hold the trip wire, small pins which will insert itself into the model. Now, suppose I have put a trip wire here. What is the guarantee that the flow here is turbulent? The initial flow here will be turbulent, but because of pressure difference, we have seen there is a relationship between pressure and velocity. Because of such pressure differences, the velocity may further drop. If the pressure difference is high, pressure is high, then velocity may drop further. If velocity drops, turbulence again may fall, because Reynolds number will, local absolutely regional Reynolds number will come down again. So, the turbulence that you created may be suppressed again and laminar flow may take over. So, it is common practice to use not only one, but maybe 2 tripwires at another maybe 10% distance or 7.5% after, it depends on the type of model, type of fullness, etc. So, this is how the turbulence is stimulated. Sometimes instead of tripwire we may use studs. Studs are, again if I draw the section here, studs are small little projections here at small intervals. These are studs, or we may use sand strips, sandpaper strips. Small sandpaper strips may be fixed at around the ship's girth at the forward end at 5% aft of AP and 10%, sorry, 5% aft of FP and 10% aft of FP to CT. And similarly, you have to have the wind resistance coefficient. Again, calculate the total wind resistance, divide by the total weighted surface, how the CT is calculated, half rho S V square. That S may be changed to S plus appendage weighted surface. Then you can calculate resistance for the total ship including that of appendage weighted surface. Then you get CTS is equal to CTS1 plus CA plus CAPP plus CAA. All this will give you the actual ship resistance either at 0 before or at before 3. The CAA will determine that depending on what sort of trial condition you want to do. Once you get CTS, you can calculate RT as half rho S plus SAPP rho S Vs square for various speeds, and EHP, effective horsepower, we have seen will be equal to total ship resistance into into CTS. Okay, and if this is in kilonewtons, this will be in kilowatts. This is in meters per second, this will be in kilowatts. Now, you have to be careful because the whole calculation we have given is in newtons. So, somewhere along the line you have to convert it to kilonewtons, maybe dividing by 1000. Okay. So, this is the way you have to extrapolate from model scale to full scale. We will stop here today. Thank you.